All right, so today's lesson is just what is this new thing that we're talking about, because you've never seen it before or heard anything about it. So there's a lot of definitions that we need to make sure that we're all clear on. I'm not going to, on the test or the quiz, ask you to write out any definitions for things, but if a problem asks you, like, what are the vertices, you need to know what vertices are to be able to answer that question. So this vocabulary needs to be known to be able to do things. So what graph theory is it has these things that are called vertices, or the singular is vertex, and really those are just like dots. Okay, so we're going to have dots on there. Then it has lines, which we call edges. So at its most basic, the idea of graph theory is connecting the dots. Okay, so we're going to have dots, which we are going to call vertices because that sounds a little bit more formal. And then we're going to have lines, which we're going to call edges, and they're going to connect the dots. And we're going to learn a lot of different things about how connecting dots can be helpful with lots and lots and lots of different real-life applications. Like this unit is totally applied math. Okay, so we're going to be doing a lot of applying to real-life situations here. A graph, it says, strictly shows connectivity, not necessarily locations or distances. Okay? So that means that when we draw a graph, we can just put these points wherever we want, and we can connect them in appropriate ways, and somebody else may have put their dots in different places, but connected them the same, and that's okay. So locations and distances are not important in drawing a graph. And that actually ties down to a word down here that says isomorphic. Isomorphic means that the two graphs are really the same. They're showing the same connections, they're showing the same vertices, but they were just drawn differently. They were just arranged differently. And we'll do an example that shows like what that could look like, what two isomorphic graphs could look like. A simple graph, it says, does not allow for multiple connections between the same two vertices. So typically, we are going to work with simple graphs. And that means if I have 2 points, I can only connect those 2 points once. In a non-simple graph, it would be okay to make another connection between those 2 points. We'll work with some non-simple graphs, but mostly we're going to work with simple graphs. The order of a graph is the number of vertices it has. So how many points are in the picture? That's called the order. The degree is how many edges are going into that point. So we can just count up how many edges are going in there. If two vertices are connected, we say they are adjacent or neighbors. Adjacent is just a fancy word that means next to. Like I could say my class is adjacent to Mr. Bell's class. Just means next to. So 2 points that are connected are adjacent points or neighbors. A graph is complete if every edge you could possibly draw is drawn. So every point is connected to every point. Then we've got a walk, would just be listing a sequence of vertices, but we have to be traveling by edges. You can't just like jump from one point to another point. So you have to be able to actually make a connection there. But we just like list out a whole sequence of letters, you know, A, B, C, D, F, E, B, B, C, A. And as long as we're walking along edges, then that's called a walk. The length is how long that walk is. How many edges are we following? A trail is if we don't go back over the same edge ever again. It's like I can walk the edge. If I don't ever walk it again, then that's called a trail. A path means that I never go through the same vertex more than once. So in a path, the same letter should not appear more than once. Okay, because the letters represent the points. And then a cycle is a trail, so we're not reusing any edges, and it starts and ends at the same place, which is often going to be a good thing for us. Like, and a lot of these problems we're going to think about, maybe like actually bike trails, or going on like trips and taking a route to a lot of different places, and typically you want to like get yourself back home. So cycles are going to be an important thing for us. The distance between 2 points is the length of the shortest path that gets you there. So we said before that the length is how many edges you're going on. The distance is how do you do that the quickest. And if a graph is connected, then you can get to any vertex from a vertex by the means of paths. That doesn't mean you could get there just like in one step, but at some point you could get yourself there. Okay? Lots of words. We're going to apply those words to the pictures at the bottom, but first we're going to play a little game. So, first question says, is this a simple graph? So the graph of simple, or the definition of simple says, it does not allow for multiple connections between the same two vertices. So if we can find any 2 points that are connected more than once, then it is not simple. So is this graph simple?
Yes.
Yeah, the most times anything's connected is just once. So this is a simple graph.
I don't understand what.
I don't either.
So a non-simple graph, an example of what a non-simple graph would look like. So I've got some points, things are connected, but maybe something is connected more than once.
Oh.
So
Is it always going to be like
this
half?
creates a problem. If we have 2 connections or more between the same 2 points,
Gotcha.
that makes it non-simple.
Wait, don't erase that.
Oh, good idea. John.
Right, what is the order of the graph?
6.
So the definition of order is how many points or vertices are there? There are 6. The degree of each vertex. So I'm going to go around and just label it in the picture instead of labeling it out in the question. But the degree is how many edges are going into that point. So how many edges are going into A?
3.
3. Into B?
2.
2. Into
Two.
C?
2.
Into D?
4. 4.
Into E?
2.
And into F. Okay, so those are the degrees of each vertex. The
We
degree
add
is how
them
many
all.
edges are there. Nope, it's all individual. We don't accumulate it. We just, like on your homework, you would list it out and say like A is 3, B is 2, C is 2. Are C and F adjacent? Adjacent means that they are connected directly to each other. So are C and F connected directly to each other?
No.
Are A and F?
Yes.
Yes. Okay, adjacent is they are neighbors. There's a single connection that can get you from one to the other. Is this a complete graph? Complete means every possible edge that could be drawn in is drawn in.
No.
No.
It is not complete because, for example, C and F are not connected. And if it were complete, they would be because everything would be connected to everything. So this is not a complete graph. So then it says, is there a complete subgraph? And if so, where? So what I want to do is find, could I just like think about just a few points at a time and have there be a complete graph? And I heard some yeses. What would be an example of a complete graph?
A, D, and E.
A, D, and E are all totally connected to each other. Are there any more?
Yeah. B, C.
B, C, and D are a complete subgraph. It's often pretty easy to find a complete subgraph of 3. Once we start to get 4, that becomes a bit trickier of a thing. And there are not any complete subgraphs of 4 in here. Okay. And then it says, draw a graph that is isomorphic to this one. The important thing about isomorphic is all of the connections need to be the same, but the points can move anywhere. So sometimes when we try to make a graph isomorphic, we're trying to make it so that it doesn't overlap itself at all. So kind of like our circle game, we're trying to kind of untwist and unwind the graph if possible. It's not always possible to do. And that's what planar means, that it can be drawn without any of the lines crossing each other. This one actually can be drawn as a planar graph. If we would think about just kind of grabbing some of these points and dragging them around.
You dragged A down.
And
You put
F
A
to the other
down.
side.
So
No, if you just dragged A down, then F would.
if I
would
drag
come out
A
also. So it'd just be A
down, you said, so that's going towards the bottom now.
That'd be it.
That'd be it. Because then it would bring F down.
And
Yeah, it'd bring
then,
all of them down.
so D and E are going to stay where they are.
F was gonna stay where it is.
F stays
This
where it
one
is,
would
and say B and C can stay here. Then we have to make sure we make all the same exact connections. So A should be connected to F, and D and E. D and E should be connected. Then we should have that complete subgraph of B, C, D. And so this works. We have the same two triangles that we had before, and we have that same extra line from A to F that we had before, but the triangle's kind of flipped upside down.
Okay, so I just in my mind I took the triangle BCD and just like flipped it
And
over.
rotated it down or flipped it over, that would work too. Yep, so and that would be another isomorphic graph. It's exactly the same connections, the points are just located differently.
I'm confused on how what you just did at the bottom. I don't know what you're doing.
Basically what I did is I grabbed point A and said, let's move it down to the bottom with all of its connections.
Well, how does that help at all?
The lines aren't overlapping each other anymore.
Oh.
So my new
Okay.
graph, nothing's crossing, so it's a little bit more clear what's connected to what.
Okay.
And that's not always possible. It's always possible to draw an isomorphic graph. You can just move the points around, okay? And it can be just as messy or messier than even before. So it's always possible to do isomorphic. You just move stuff around, but all the connections have to stay the same. It's not always possible to make it planar. This one is now called planar because there's no crossing lines. But if you can, that can often kind of help us clear up a picture. So in your homework, if you're asked to draw an isomorphic, you might want to look and see if it looks like that might be possible, and if it is, do it that way, and if not, then just redraw it some other way. Next one says define the pattern of the vertices. So what we're going to do is start at the first letter and then just kind of follow along and see which one of these patterns it is. Our words, this is that big paragraph where we can say it's just a walk, it is a trail, it is a path, or it is a cycle. And those are the things that we could call this. And we want to be most specific as possible. So something's a cycle, it's technically also a trail and also a walk, but the cycle is the biggest deal. That's the most specific. So if I start at F and go to A, and then to E, and then to D, and then to B, and then to C. What would we call that?
The trail.
It is a trail and a path. Yep, we didn't reuse any letters and we didn't reuse any sides. So that one we should call both a trail and a path because those are distinctly different things. One talks about vertices and one talks about edges.
Is this for number 7 or 8?
It's for 7. 7 actually has 3 parts there, so that's the first thing for 7. So I'm going to erase my tracings here. Try tracing up the next one. So for the next one, start at C and go to B, go to D, go to E, go to A, go to C. Problem. I can't, right? I cannot get myself from A to C, so this is actually not possible. That's not anything. It's not even a walk. A walk is the most general thing, and it's not even a walk because I can't walk myself from A to C. Not directly. I could get there going through other stuff, but I cannot directly walk. All right, and then the last one, B to D, E to D to B. What is that?
Cycle.
I ended where I began, but a cycle has to be a trail. And what does a trail mean?
But it's not.
I can't repeat any edges, and I definitely repeated some edges.
So it's just a walk.
So this is just a walk. That was like taking a walk out into the woods and then turning around and like walking yourself exactly the same way back. It's a walk. You didn't follow a trail or a path through the woods. You just walked and then you turned around and walked back. So all you did was walk. Okay? The distance between 2 points is the fastest way to get from one point to the other point. So how fast can I get from C to F? C, D, A, F. Looks like the fastest way I could get there. I could go also C, B, D, A, F, but we want the fastest way. I can't get there in 1, I can't get there in 2, but I could get there in 3. is the graph connected? Connected means that I can get from one point to any other point through any number of steps. So is it possible to get from everywhere to somewhere else, at least by traveling through it?
Yes.
Yeah, that is connected. When you have a disconnected graph, you will have what we had with our two circles. Those were disconnected graphs, okay? Because you as a vertex, there were some people that there was no way you could connect yourself to because they were in the opposite circle, okay? So a disconnected graph will have different groups of points that you can't connect, all right? All right.